Hello, everybody. This is Roderick Tambek Gimfak. I'm presenting my final project for CS 8673 Machine Learning with Dr. Mittal. My project is about transfer learning. In the next slide, I will talk about agenda. I will start with the introduction, motivation, and concepts, methodology, algorithms, also data set, and I'll finish with some application on the real world data. What is transfer learning? Well, transfer learning has recently attracted significant research attention as it simultaneously learns from source domains which have plenty of labeled data and transfer the relevant knowledge to the target domain with limited labeled data to improve the prediction performance. The goal of this project is to use many transfer learning methodology and in particular deep Bayesian transfer learning to build a machine learning that will be able to accurately predict whether a patient is COVID-19 positive or not, given an input data chest X-ray. Clearly, this is a classification type of problem in data science jargon. As we all know, most machine learning algorithms correspond to supervised learning. Working in isolation work well only under a common assumption that training test data must follow same distribution. When distribution changes, most statistical models must be reconstructed from new collected data, and that may be in general costly or even impossible to get depending on applications. It becomes necessary to develop approaches that reduce the need and effort demanding for few labeled samples by exploiting data available in a related area and using it further in related field. Then you can see that this gave rise to a new family of machine learning algorithm called transfer learning. See, the situation is we have a new situation where we don't have a high quality trend data. And what can we do to address that kind of situation? For example, with COVID-19 being a new disease, there is not sufficient amount of medical label just array. What I mean sufficient in code, because if you want to compare COVID-19 with a disease that be around like diabetes and others, you can see that COVID is quite new and we don't have a bunch of data. So it becomes necessary to develop approaches that reduces the need and effort demanding for new label samples. Having a well-designed machine learning system without the need training data is like having a sport car without energy. So that's just some analogy. Well, let's talk about motivation about this project. There are many reasons why I am interested in this project. Perhaps the most important reason is that more than 600,000 people have died from contracting COVID-19 in USA. More than 600,000 people and millions around the world in general. It is critical that we use our analytical skill gained from taking these courses to contribute as much as we could to save lives. That was my main reason. Another reason is that part of my thesis as a requirement by the graduate school is about transfer learning, domain adaptation. For that reason, I decided to work on transfer learning for this class project as well. So, talking about transfer learning, as described by Mr. Wang in his book Survey of transfer learning deals with how systems can quickly adapt themselves to new situations, new tasks, and new environments. It gives machine learning system the ability to leverage auxiliary data and models to help solve target problems when there is only a small amount of data available in the target domain, which is the ideal case for the COVID-19 project that I'm working on. This makes such system more reliable and robust, keeping the machine learning model faced with unforeseeable changes from deviating too much from expected performance. There are many transfer learning methodologies that exist. In the next slide, I will show the diagram or the big picture of the methodology. So, transfer learning, we have inductive transfer learning, transductive transfer learning, unsupervised transfer learning. In this project, I'm mainly concerned with transductive transfer learning. What does that mean? It means that we have a source domain, a source data or domain, and that has a distribution that is not exactly the same as the target domain. So the target domain has a distribution that is similar but not exactly the same as the source domain. Yet the tax on the source domain, it might be the same thing as the tax on the source domain. So that is the transductive and transfer learning, and that's the object of this project. So just to reiterate, this project deals with transductive transfer learning. That is, the model exploits the labeled train set and unlabeled test set for train the model to infer the label on unlabeled tests. There's a library called Keras that provide a range of pre-training models that can be loaded and used wholly or partially via Keras application API. A useful model for transfer learning and the one used for this project is VGGNet model. In particular, I use VGG 16 with 16 layers that at the time it was developed and achieved a top result on the ImageNet photo classification challenge. So it's a powerful model. The model is comprised of two main parts: the feature extractor part of the model that is made up of VGG block and the classifier part of the model that is made up of fully connected layer and the output layer. We can use the feature extraction part of the model and add new classifier part of the model that is tailored to the COVID-19, positive or non-positive. Specifically, we can hold the weight of all the convolution layer fixed during the training. So this way achieved by loading the VGG16 model, removing the full connected layer first and of the model, then adding the new fully connected layer to interpret the model output prediction. Let's talk about weight initialization. In the weight initialization, I use a deep prior. So what is a deep prior? A deep prior employs a new type of prior distribution for convolutional neural network. DWP, which stands for deep prior, exploits generative model to encourage a specific structure of trained convolutional vectors, spatial correlation, prior distribution of convolutional neural network. I'm not going to talk about generative model. We discussed a lot during the course of this class and done some homeworks and it's on the final. So generative model is well understood in this course. Bayesian approach. And for this project, the Bayesian approach that I use is a classical Bayesian approach, meaning that we have a prior distributions of the weight and we have the likelihood, and the goal is to predict the posterior distributions. Well, predicting the posterior distribution is analytical difficult. I would say computationally expensive. So instead of trying to predict the posterior, we're trying to approximate that posterior distribution, and we'll talk more in the next coming slide. So Bayesian inference, to start with, it uses a Bayes rule, meaning that we have a likelihood and we have the prior distribution, and the Bayes rule infers that the posterior distribution is the product of the likelihood multiplied by the prior, and then we just scale it by the probability of the distribution to have a probability that makes sense. Methodology of deep weight prior. Bayesian inference, known to provide general framework for incorporating prior knowledge into machine learning model via careful choosing prior distribution. DWP act as a prior distribution while training on new data set. That's how we train, using some prior distribution for the weight. And as I mentioned, DWP was used implicitly as a form of implicit distribution. And in the end, it improved the performance of the Bayesian neural network by initializing, by weight initialization, and by the weight initialization, yeah. Consider implicit prior distribution in the form of a variational encoder. So yeah, we actually, in order to use the weight initialization as a prior distribution, we use a variational encoder that I will talk much more in detail in the next slides. So, talking about variational inference, if we have a situation where we have a Bayesian computation, and as I mentioned, we have a likelihood, the prior, and the objective is to figure out the posterior distribution. Instead of finding the posterior distribution, it's smart to instead approximate that distribution using the divergence-Kullback formula. And then, so the problem of maximizing the likelihood is the equivalent on minimizing that likelihood. And then in the next slide, I will talk a little bit here about how, in general, that works. So we train the CNN on the given source data D1, collect the data S of learned kernel, train a prior distribution on S, use the distribution for Bayesian inference on the new data set. That's in nutshell what happened. Again, there are generative models which help to generate similar type of input data, image, text, etc. as we learn in this course. So generative model learn data distribution of input data so that it produce new similar data. That is one question on the final. And it is also make a probability distribution of input data, and from that distribution you can create new samples, and that's the beauty of generative models. As I promised that I will come back on divergence-Kullback theorem. As you see on the formula, the Kullback divergence theorems has two major terms. The posterior approximation of the probability that we want to have, and the log of the ratio of the probability and his approximation. If you see that ratio, if we approximate correctly, then the ratio should be close to 1. In the ideal situation, it should be 1. If it's 1, then we will have log of 1, which is 0, and the product of 0 with anything is going to be 0. So the divergence will be 0, meaning that the two distributions are exactly the same. Well, unfortunately, in real life, thing is not that easy. This divergence is always greater than 0, and that is not surprising. We are not aims to have a 0 here. We just want to have something close enough. As I illustrate that with that image on top, we have a 2L And we can consider that those two hill mountain as two distributions. And the green distribution is actually the posterior distribution that we are trying to get. But we, instead of looking for that, we can approximate with the red distribution there, and which is approximately good enough. I also mentioned that this diversion, Klubat is not symmetric. It's an important problem to property to have. Talking about the data set, this data set was collected on Kaggle and is publicly available. We have a 215 positive case for COVID-19. As you can see, it's very such of small data, and we have about 1,000 non-positive case. And this is ideal example of small data in in transfer learning. Always know that deep learning is hunger of data, but what happens if we don't have a data? And that's the object of this presentation. So the first deep convolution neural network that I worked as a base model was just CNN and VG4 with some regularizations. It actually was really performed very well, as you can see from the learning curve. But the thing is, after the six epochs, it start overfitting, as you can see there, and this is because of such of small data. Um, Having such of small data is not easy to overcome the overfitting just by regularization alone, and that's why we're trying to go on to transfer learning to solve that kind of issue. The classification report for this base model showing a F1 score of 91, which is pretty amazing. It's not bad. And the confusion matrix with 21 misclassifications. And the ROC curve showed about 95% accuracy. So it's not a bad model, but showing from the learn curve is showing some improvement that we can actually have. And that's the reason why we trying to leverage the transfer learning methodology. So let's talk about the transfer methodology. Here is the learning curve after using the transfer learning methodology. This curve showing that there's no overfitting. The model is more stable and robust. And the learning curve is for the validation and training is pretty much is pretty close all along. Let's see the classification report. Oh wow, the F1 score is about 0.99, which is so amazing with such a small data set, about 200 positive case. And the ROC curve show about 0.991 accuracy. The confusion matrix show us that we only have one misclassification compared to the model that we have before with 21 misclassification. In conclusion, in this work, I use a deep weight prior, a framework for designing a prior distribution for convolutional neural networks that explore prior knowledge about the structure of learning convolution filter using real-life COVID-19 chest X-ray data, about 1,000 samples in total. The baseline model using the VG4 with such a small data set was able to get us an average F1 score of 91%, which is relatively great. However, applying a transfer learning methodology with deep weight prior, we achieve a 99% F1 score, and that is about 11% increase in F1 score compared to the CNN with Jeff regularization. Now, even though this particular data leverage transfer learning help improve the predictive power of our machine learning model, a lot still need to be done in terms of applying the same methodology across different data sets to see if the conclusion actually hold. And this is something that I'll be happy to continue working on even after this course. Next is just a reference, and any question I'll be happy to answer through my email. Thank you for listening. Thank you, Dr. Mitchell. I had a great semester. I learned a lot, and you have a great evening. Bye.